you the actual assignment, but usually find them the links for some reason aren't working. So here's assignment 4, and there is assignment 4 input that goes with it. So if you go up here to actual assignment, it's not published. It's so awesome.
Oh, wow.
Sorry, I can't stand you.
Nice one.
Say it again?
It was on 5.
Okay. Yeah, so the files are actually linked here to assignment 4, but your assignment is published. So there's the link to the document. So assignment 4 is due on April 19th. So that gives you about 10 days to get done. And we're going to have an assignment 5 also that will be out very soon. That we do, I don't know. I got to do it. What? Not good. It's a good assignment. So I'm going to stack assignment 5 on top of this because this is final week. No, finals are actually like the week before. Finals start this week, so we have it due Monday is an actual class day, the 28th is a study day. So finals actually start on the 29th. So I'll make assignment 5 is due on the 28th. And I'll get that published this week so that you can have them rolling. So let's go over the assignment. Okay. So when you look at the assignment, there's a lot to do. This time, instead of doing a link search, we're doing a binary search tree. I'm saying specifically a binary search tree. So what's the difference if it's not just a binary tree? It has to be in a very specific order. What is the specific order for binary search tree? Everything to the left is less than the root node, and everything to the right is greater than the root node. So when you read in the data file, you have to make sure that you create that binary tree correctly. So here in our main, we have 14 different options. You're like, oh my God, that's a lot. But not really, because about half of the code is on web courses that you have in the table. So it's not like I'll put it on your own. Because code is already there. The stuff that come up with on your own, though, is starting at option 7 through 12. But again, there's going to be, there are examples out there. So what you're going to do is you're going to read in the data file, and that's going to happen on option 1. So you're going to read that data in, you're going to generate a binary search tree. So here, you read in your data, and then the next thing you're going to do is we're going to display in the 3 different formats: the pre-order, the in-order, and the post-order. So what is the methodology we have to use in the binary tree when we're talking about pre-order, in-order, and post-order? So there's 2 types. Depth first, correct. So when you do a depth first search on a binary tree, what is that telling you? How is that tree searched when it's depth first? Which side of the binary tree gets searched first?
Left.
The left. So when you do a depth first, you're going as far
Left.
as possible until you find what?
Left.
A leaf node. Because what tells us it's a leaf node? Has no children. So what is the value of a leaf node left and right? No. Okay, so just like a linked list, we know it's on the end of our linked list because the pointer to the next is null. The same thing is true in our binary trees. We know that a node is actually a leaf because its children, its left and its right, are both null. Okay, so there's a lot of consistency there, and that's why at the beginning of the semester you really need to understand linked lists, because linked lists pretty much drive us for the rest of the semester, because without linked lists, we find the search trees is really hard. When it's like, holy crap, and I got 2 things to keep track of. So this, we can get through that process one step at a time. Okay, so first you're going to have a function that reads in data from a file. And so we've done this for every single assignment in the semester, so hopefully you're comfortable with reading data from a file by now. And what you're going to do is, as you read in that data, you're going to generate a linked list. How about a binary search tree? Let's create a binary search tree out of it. We're going to read that data in. And then, once you read that data in, then we have our different traverses that we're going to use to look at a linked list, our binary tree. So first, where is my data file? It is. So assignment for input. So here's the data. There's 25 items in this binary search tree. So if I'm doing a binary search tree, you have to read the data. You have to display it in this order. What is the value of 50 going to be for your binary search tree? It's the root, correct? Because that's the first guy that gets put up there. So when you're considering how do I do that, let's go back to actually the slides from Monday. The search and insert. Remember on Monday we were talking about that? How we're going to generate a binary search tree correctly? And so from a visual perspective, this is what it's going to look like. And then if you go through the code that is available here, so there's code in the slide, and then there's also the binary tree.c example code that's uploaded as well with the code examples. So you have lots of examples of how to accomplish this graph. So here, this is the searching because you're looking for a specific node, where here is the insert. And so here's an example of an insert. First of all, here's our struct, where we have our data portion of our node, and then we have our left and right. And then when you want to actually start creating that binary tree, so this function here, it does create node, you get a value, whatever the data value is, and then we're just returning back a pointer to that node so that we know where it's at. And so here, you see that we allocate space, so just like the list, we're using this guy temp to help us through. And then we're going to do the malloc. Don't forget to do the malloc. This is where a lot of people are getting errors with their code, where it looks like it runs 3-4 times and then it crashes and they don't know why. Because C is trying to do the right thing, but after it starts to get 3 or 4 nodes that aren't properly initialized, it goes, I just can't, I'm done. Okay? Make sure you malloc. Because if you don't malloc when you're trying to access the members of that struct, it starts to kind of go, oh, I'm so confused, okay? So here we set our data, we're going to automatically set our left and our right, just like we did with the list on the next. As soon as you create that node, set its next to null. So here, as soon as you create that node, set its left and its right to null, because you don't want to have any weird data coming out there. Yes, sir? Very good, yes. Now is your friend. And then here, this is how we're going to turn the pointer back to our created node. So if you guys are not happy with using a double pointer, some people are going, let's just make asterisks, I can't do it. That's fine. You can use single pointers as long as you pass them back correctly, okay? So just make sure you don't lose that reference, because if you lose the reference to the root, it's just like losing the reference to what in the linked list. Just like losing the head, right? If you lose the head of your linked list, where's your data? Who knows? It's out there somewhere, and I can't get to it. Okay, so don't lose the reference to the root. That's very important. So here's just showing you how to properly insert into a binary tree. So for our homework assignment, it says our value is 50, but here it's 10. So that's your first node, you create your first node. And then you start doing the evaluation as you're inserting into the binary tree, when you have to actually go through and determine where that next value goes. So in this case, we have a 14. Why are we putting it on the right of 10? Because it's greater than. Because we're doing a binary search tree. We're doing a BST. We're not doing a binary tree. So then here, here's my data file. So if 50 is our root, where's 21 one's going to go to its left, because it's less than 50. Okay? So then you keep doing that process as we go through. So there's 25 nodes binary search tree. Okay, so you're going to read in that data file, and you're going to generate your binary search tree off of the data in that file. So you just read the data in sequential order. There's no added to it or anything. You just have to read it that way. And so after that, then we're going to have a whole bunch of functions that are going to exercise all the functionality that we can do with the binary search tree. So the first thing you do is you're going to print your EFC in pre-order format. So in pre-order format, what is going to get printed first? Pre-order. What gets printed first? The root node, right? All right, think about the root node as an output, and the output's the ATM, and you have to go get money before you buy drugs, right? Okay? So, and then from that point forward, we would print what? On a pre-order. What do we do after the root node? Print the left and the right. What if the left's in the child? You go all the way down. You do the traverse. You do the leftmost traverse until you find what? A leaf. And then you can start printing, correct? If there's children, you don't print that node until you get to an actual leaf. So here, so if I was doing a pre-order display of the nodes of my binary search tree, what value is going to get printed after 10? Pre-order is what? Left and right. But left what? The very next left? Is it 6? Do I print 6 next? Why not? Yes, it has a child. It's not a leaf. Okay? Yes. So you have to make sure that you traverse all the way down until you find a node that's a leaf. That's how you find your leftmost leaf. What is our leftmost leaf? Or in this case, what is a 5, right? Does he have a left? No. So if that's the case, we have no left for something to print here. Correct? So then we're going to print what? If there is no left, we do pre-order. So 10, then 2. That is, do the parent first, right? So it doesn't matter how far down you go. You do the parent first. We found the leaf. 5 is our leaf. Because we're saying pre-order means we have to print the root node first. From this relationship here, at just this level, who's the root node? And who's the parent? 2. You print the parent first. So we're printing our 10. We get all the way down to our leftmost, there's nothing there, toward 2. Print. So we have our 2, and that's to the left, and then it's to the right. So 10, 2, 5. You guys heard of that? Does that make sense? Let's look at let's go back to what we're doing on here. Remember we went through this process on what, Friday? Last week Friday? On Monday? We went through this? Pre-order. What's get printed first? Pre-order, so it's a 3, correct? What's next? We do the root, the left, and the right. Who's going to be printed after my 3? 26 or 54? Why 26? It's a parent. Remember, we do find all the way to the left, find that leaf. We found our leaf, 54. But we're we have to print his parent first, don't we? So that would give us 3 instead of 26. And now we can do the left and the right. 54 and 71. You guys tracking? You really should go look at these, because the good thing about these is we have our that's the solutions here. So as we go all the way down. So parent first, so 3, he's a parent. Then we look at our 13. Is he a parent? Yes. Now we're doing pre-order. So parent gets printed. Is he a parent? Yes. What about his left? Is his left a parent? Yes. Print him. Is his left a parent? Yes. Print him. Is his left a parent? Yes. Print it. Is his left a parent? No. So now we can start doing our left. So look. See here? I want these slides at the same time. I thought I could open two of these. Bear with me. Give me the damn answer. Alright. And it was a little hard to see text, but I get it. Okay. So, pre-orders. Parent, 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 parent until we find the left. Parent is 3, parent is 13, parent is 22. 22 has a 19, he's a parent, he has a child, 26. 26 is a parent. His leftmost node is 54. So then we look at the pre-order. So if we're printing this, we print all the parents first on the left until we run out of parents, and then we're going to start doing the left. And so here our lowest parent is 26. So once we hit 26, then we can start printing our left. And so then we do our 54 and then his right. And then we go up. 26 has already been printed because he was a parent. So the left of 19 has been dealt with. 19 does not have a right, so there's nothing to print. So we roll back up to 22. We've dealt with 19 as a parent on the left, so now we just print our right. And our right is going to be the 9. And then we look at 9 and go, oops, well, does he have a left? No, if he did, we print it, but he doesn't have one. So we print our 75, and now we've dealt with the right of 13, and so now we can roll up to our 3. We've completely exhausted the left side of a binary search tree, so we're going to go to our right now because it's pre-ordered. So we did everything from the 3 and the left side, so now we go to the right. And the right is 28 a parent? Yes, print him. What about his left? His left is 15. Is 15 a parent? Yes, print it. We're going to go to, what is his child? He has a left, which is 10. Is 10 a parent? Yes, print it. Then we get down to 63. Is 63 a parent? No. We found a leak node. Okay? So then we're going to go ahead and print our left, which is 63. Does 10 have a right? No. So we're done with that one. Now we roll back up to the 15. We've dealt with 15's left already with the value of 10. So we would print his right. There is no right. So we roll up to 28. We've dealt with 15 as the left for 28 already. So now we need to go to his right. And so his right is 36. 36 is parent. So you go to each children, and is his child 7 on the left a parent? Yes, he is. Print him. Does he have children? Yes. His child is 69, so you print him. And then finally we get to the note. We have our lead node here. So 69 is printed as a parent, so we do his left and his right. So we do his 59 and 68. 69 is dealt with as a parent, and he is the child of 7. Next we will do the right of 7. There isn't one, so we skip it. So then we go up to 36. We dealt with 36 left as a parent is 7, and so we're going to go over to our right and start dealing with our right. is 36 apparent? Yes, you print it. Look at his left. Does his left apparent? Yes. So print him. Is 69 apparent? Yes, you print him. So then you look at his leaf nodes and you're done. You find out that you're at the end of your binary search tree. So then you print his left and his right. So you're 59 and you're 68. Roll back up to 69. 69 has been dealt with as a parent. So from 7's left step, we were finished. So we're going to 7's right. 7 doesn't have a right, so we're done with him. We roll back up to 7. 7 has been dealt with as a parent, so he's already been printed. And so he is the left of 36. So we go ahead and print our 44 to get our right. And then we roll back up to our 28. We dealt with that whole right side of 28. And so we are finished with our tree. So again, tree order is parent first. So if I take that away, when we're talking about in order means what? What gets printed? When is the root node accessed? In the middle. So you do your left, your root, and then your right. So we go through the same process. So this is one of those things that when you are doing the homework assignment, go look at this data, and then go to these slides and look at the practice problems and make sure you understand how that data is supposed to be printed out. So you just need to be comfortable with that so that if you're asked to write this out, I mean, it's really easy to go look at the code examples and reuse them, but you actually understand it. And whether or not you understand it, making yourself understand it, everybody's different, but if I write it down, I'll remember that. If I just look at it, I don't know, I'll probably forget. But the one thing that puts information in my brain is either I typed it or I wrote it down. Then it's like fed into my brain and I remember. So just make sure you use these slides as a guide to get through assignment 4. Okay, so you're going to have a function that displays the BST in pre-order format. And then you have an in order and then the post order. So when you're doing post order, what is the root node access? Slash, right? So you have to go through. So again, go back to those slides, walk the trees, traverse those trees, make sure you understand. And then here you have a function to display the BST in breadth first format. So if I was doing a binary tree in breadth first format, how would I traverse this tree? If I'm doing breadth first. What node is first? The root. Then what?
28.
What numbers?
28.
28, 13. Then, okay, so you go level by level, correct? You just do a level by level, left to right. And you don't care about parent-child relationships as insignificant from a printing perspective. You just merely go from left to right all the way down the tree until you run out of nodes. Does that make sense? Okay, so we need to find a value in a BST. We have to search for a BST, a value in the BST. And so here I have two test cases. The one is to search for a BST, a value that exists, and then search for one that does not exist. And make sure that if it finds it great, if it doesn't, that you usually know that value is not in there. So when you're searching a binary tree, this is what we talked about on Monday. So once we actually create the tree, now we can do stuff with it. So this is just a binary tree search. So what's unique about the binary tree search versus a binary search tree? So it is just a binary tree. What way are you going to look at the data? Do you really care what order it's in? Right. That's the thing about binary trees. They don't have to be in a specific order. But if I told you you need to do a binary search tree search, is it faster or slower than just a regular binary search? Faster. Why is it faster? Because you only have it. You have it immediately, don't you? you compare the value you're searching for to the value that's stored in the root node, you automatically know which way you're going. So if you're doing, if our root node is, if I ask you to search for the value of 27, where would I go? This is not a binary tree. Is this a binary tree? That's a binary tree. It's not a binary search tree. Neither one of us are binary search trees. Why are they not binary search trees? What's wrong with the data? Yeah, so our root node is 3, and then we have values that are greater than 3 on the left. So that doesn't meet the criteria, does it? Okay, so we're going to do a binary search tree. So pretend this is actually, change 3 to about 14. 14 out there? Yeah. 15 over there. 16 of them? Alright, imagine 3 is a 16. We're getting a little bit close. No, it still doesn't work. Anyway, alright. Let's pretend this is a binary search tree. Alright, so we have the value of 3 and the root node, and I ask you to search for the value of 98. Which way are you going to go on this tree? You go to the right. Why are you going to the right? Is greater than the 3. Okay? So we are specifically doing a binary search tree. You have to be careful and make sure you pay attention to the requirements, especially when you're doing a handwritten exam or maybe a foundation exam. Make sure you're paying attention. Is it specifically a PLC or is it just a binary tree? So here, this is the code for just a binary tree. If you don't care about the left or the right relative to the root, the data's just there. So we can do a return on the left and the right at the same time. So we're just looking to see if our current value is there. And so we're going to search our left and our right simultaneously. Do you remember when we were talking about doing recursion? So we had this splitting of the halves. This is an implementation of recursion of half and split. You guys remember that? Maybe? You thankfully forgot? Let's get out of my brain. Where was that? That was up here in recursion somewhere. Well, here. So it's in the slide deck as well. So splitting the range in half. And you see here that when we actually do the recursion, we are calling one side and we are calling both sides at the same time. So if we look at the code for that, which is up on web courses, we'll look at the recursion code. Okay, so right here. This is the split recursive sum of squares. See that? Calling them both simultaneously. So this does have a purpose. Binary tree. Okay? So this is what we're doing. Here. This is the splitting of the half. That's entirely up to you. If you think that that code is correct, then by all means. You just want to make sure that you get it right. So here you can see that this does not care that we're searching a binary tree because it's doing the splitting of the halves and it's calling both sides simultaneously. And so it's stacking the function call on the stack because the stack is the function call until it finds its value. Okay? You see the relationship between this and the splitting of the half and the recursion? Yes? Maybe? Okay? Okay. So here is the extra stuff above and beyond what has been provided for you in code examples. So here you're going going to find a value in your BST. So the fact that we are doing a BST and finding a value, would we use this methodology?
No.
Why not? We only need to search either the left or the right, don't we? We don't need to search both. This is searching both. Okay? So we don't want to do both. We want to do one or the other. Doing one or the other, if you look in our binary tree example here, here's our search. This search is written specifically for a binary tree. How can you tell that by looking at this code? What is the key factor to this search algorithm right here when we're doing if, else, and if, else, if? So, how are we searching the tree? What are we checking? Checking our value against the left or the right. Because there's only one possible way to go on a binary search tree, correct? This is what makes it different from just a regular binary tree and searching the binary tree itself. When you're searching a regular binary tree, you can do the left and the right simultaneously using that splitting of the halves methodology for recursion. Here, we are very specifically looking for a value, and we know which branch of our node we want to search through because relative to root, that value is either greater than or less than root. So that's what this code right here is doing. It's comparing that value equal to whether or not it's on the left or the right. You see here, if our value is less than the value of our data in our tree, then we are intentionally searching the left only. The second one here, we have our else if. It says, hey, if it's greater than the value that's in our tree, then you can go to the right. So we're only going to search that right. Otherwise, we're going to come down here and it equals. So if it's not less than, it's not greater than, it must be equal. Correct? We come to that assumption. So if that's the case, then we just go ahead and return that node. So what would we call that last else if leg in this code from a recursion perspective?
Base case.
It's our base case. Thank you. Why is it our base case? What is the overall definition of the base case? What happens to recursion?
Stops.
It stops. Do you see how this recursion is stopping when we find our value? How do you know it's no longer adding a recursive function call to it? How is it different than the other two parts of our algorithm? It just go ahead and return the answer, doesn't it? That's your base case. Your base case just returns that answer. Whereas our other two conditions here, the value being less than the value greater than, it just turns it on, does another recursive function call, doesn't it? You see you see that function is calling itself. You scroll up to the function definition, that's our function, right there. So this implementation uses double pointers. So if you're going to use a double pointer methodology, you have to dereference it to get back to a single pointer on that node. So make sure if you do use double pointer notation that you understand what you're doing. If it's a little too much, then just do the single pointer notation and make sure you return back the reference to that node. Okay, so just be careful. Take the implementation that you're most comfortable with. Either you're going to receive and return back that node from the root perspective or the head perspective, or do the double pointer notation. So one or the other. Don't mix and match them, because you'll be like, I'm totally lost. Anyway, so here I have a double pointer, so that means that when I use my tree, I have to dereference it. Does that make sense? Okay. Okay, so here you're going to search for a value in your BST. So I've shown you two different implementations. So you're searching for a value in the BST. The code example that's in the actual online code example, the .c file I have uploaded, that's the search methodology you need. Because the one that's in our slides doesn't apply because we have a binary binary search tree, not just a binary tree. So here I want you to search for a value that exists in the tree, and then I want you to search for a value that does not exist in the tree to make sure that you're accounting for both situations. And then here we're going to create a function that finds the minimum value. So we're just going to do some statistics work on our binary tree. We're going to look for the min, the max, the average, the median, and some of our nodes, and then how many are in a ESP. So this is just a bunch of little math things that you need to do or from a statistics perspective. So there's not examples for all of it, but I kind of feel like that if you understand how to do one of them, you probably should think about it. You probably will be able to understand them all. So if you find the max value, or minimum value, averaging. So if you're going to find the average, what algorithm would you use to find an average of the data in a binary search tree? What would you do with it? Okay, so you would sum all the node values, correct? And you would divide it by what? Number of nodes. Well, what will make it easier for you, if you look at this function here, you're really finding the sum of the values divided by the count. So the function that you have to write to find the average is pretty easy if you write the other two functions first. So make sure you read through this all the way before you start coding. Make sure that maybe you can do something a little more efficient. In this case, it would be very efficient from a finding the average perspective by using the function that gives the sum of those ESP nodes and dividing it by the count of the ESP nodes, and that's your average. So median, what does median mean? What is it? Of all the nodes,
it's the middle node.
It's the middle value, right? So you're not doing any math, you're just finding that middle value and you're going to find the median for it. Okay? So then down here, the last thing we're going to do, and what we're going to talk about today for the remainder of the class, is deleting a node in your VST. And there's two test cases for it where you're going to test a value that does exist and a value that does not exist. And then finally we have our exit program, so that should function as well. So here are the specific test cases to actually run through. That's awesome. Okay? So I will create example outputs from a display perspective, but I'm going to use it as a data set for my example purposes. And so look at the binary tree code that's up here. There's a lot of it here that will help you. And then look at the slides that talk about the binary tree stuff. Okay, because there's really good information in here. Also, you can practice the traversing with your pre-order, in-order, and post-order, and your ref first. All right, so let's look at deletion really quick. About 10 minutes. Okay, so far we've done insert, but what about delete? There's two different options to delete. You either delete a least node. How do we know it's a least node? What is the value of its left in this right pointer? Null. Okay, that's the same thing as the linked list. We know we're at the end because we find a null. We're going to delete a node with one child, delete a node with two children. So, wow, how are we going to do that, right? It's very similar to the way that we did linked lists. If you think about it from that implementation, when you deleted a node in the middle of the linked list, what did you have to do with the node before that value and after that value? So if I'm the node to delete, and there's a guy before me and a guy after me in the linked list, what do I do first? To the pointer of the previous. What do you have to do to that pointer? Who's this guy going to point at? He's currently pointing at me, and I'm going to get deleted. Got to skip over to the next guy, right? You got to make the relationship between this node and this node link up, and then you can do what to that node? How do we actually delete a node in C? Free it. Yes, we use the free. Let that node go. You don't need it anymore. All right, so here, deleting a leaf node. This one is going to be easy because you just find where that node exists, right? So it's all. So what are you going to do to 14's pointer if you're deleting that node? Says what? No. Why would you set it to no? Because there's nothing there. Okay? So this is what we want to delete. So if that's what we want to delete, this is what it should look like after you're done. Are you comfortable with that? So now, the leaf node is pretty simple. But what about that guy here? We have a node with one child. We want to delete node 4. So, just like with the linked list, I have a guy before me, I have a guy after me. Who's the guy before me if I'm 4? Before me. 6. This guy is 6, and this guy is 2. What am I going to do with the 6? His left node. Make it pointed at 2, just like with the linked list. Does that make sense? So once we update his pointer, his left pointer on 6, we make that left pointer of 6 point to 2, then what can we do with the node with the value of 4? How do we delete it? Free it. Free the memory. And it's gone. Okay? So here, we want to delete 14. Okay, so I'm 14. Here's a guy here, here's a guy here. What are we going to do with the right pointer on 10? He's 10, I'm 14, he's 18. It's going to happen between 10 and 18. You're going to redirect the pointer to the next node, right? So when you get done, this whole structure right here, I have 14 and 14's left, just moves up and becomes 10 left. See that? But just like the linked list, don't forget that. Take the previous guy, the next guy, link them together, and then we can dump that node by using the free. Free up that memory. Deleting a node with 2 children. So now, this one is the most difficult one. We want to get rid of 18. But 18 has a left and a right. So like, holy crap, what are we doing with that one? Okay? What do you think we would do with it? So, I heard someone say move the 13 up and somebody say move the 32 up. So let's see what we would actually do. So we look at this, we have our 18. So we're trying to get rid of this 18. So if we delete the 18, there's only 2 nodes we could put at his position. So without having any issues, we could either pick the maximum value in the left node of 18, which the value is 15, or you pick the minimum value of the right subtree of 18, which is 25. So we have 2 options here. So which one do we want to actually implement for this to happen? Either 15 or the 22. Okay, so you pick the middle, find the min and find the max. Okay, so there's a couple of functions you have to write for this assignment to find the min and find the max. So you can use those to do the delete. So here, there's only 2 nodes you can put in this position without causing problems. And that's either the minimum value, which is 15, or the maximum value, which is 25. So we have 2 options. So how do we know which one to pick? So 15 is the largest value on its left, 25 is the largest value on the right. Really, either one of them would work for us. But if we use 15 or 25, what happens to their parents? So what do you have to do? If you're going to move 15 up to 18, or you're going to move 25 up to 18, somebody else is depending upon them, right? I mean, think about like taxes. Your children, they're tax write-offs, aren't they? Okay? You don't want to lose your tax write-off, but you have to keep track of that. So how do we know which one to use? And so in this case, we would use, we're guaranteed that knows that 15 in this example, and it only has one child to the left. So 15 is greater than 13. So we can use that implementation. And then 25 will also yield that same response because 25 on the left is 13, which is less than, on the right is 32, is greater than. So we're still following the correct methodology regardless of which one we use. So here we just have to look at how many children they have. How do we know which one we should use? So let's look at this. So in our BST, we have 18 is the value we want to delete. So now we have to pick which one we want. So in this example, we're going to go ahead and pick the value of 15. Well, we do the evaluation of which one is the greater than the left hand. So here, his largest value is 15, and his largest value is 25. So then we go through the code, and we're going to try and determine what's going to happen. I have 20 after, so we will finish